So up to this point in the course, we've talked a lot about limits, and we have to really lay a good foundation for limits, because everything from here on out, when we talk about derivatives and integrals later on in the course, everything is based on the limit. So it's really important to get a good foundation of limits. Okay, so at this point in the course, you should have a good conceptual understanding of what a limit is. But in this section, we are going to transition that intuitive understanding of a limit into a rigorous formal definition using precise mathematical language. And a lot of students struggle with this the first time they see this, and it's totally fine, it's totally normal, don't panic. It takes time to practice. I'm still trying to get good at this as well, so don't feel bad. This isn't going to be a major part of your exams, but it is important to cover this because, like I said, limits is a huge part of calculus. Everything in calculus is based on the idea of the limit. So it's really important to make sure that we cover this so we have a good foundation. Okay, so the first thing I want to do with you is I want to discuss and walk you through the definition of a limit. I'm going to explain what all these symbols mean, and we're going to break it down phrase by phrase. And then I'm going to walk you through and show you this animation so that once you understand what the symbols mean, then we can make the connection conceptually what it means on the graph using this animation. So we're breaking it down step by step for you. And then we've got 5 examples that I'm going to walk you through step by step. Now, this is also a difficult section because for most of you, this is going to be an introduction into proof writing. Officially, we are going to be writing some basic proofs in section 2.5, and there's kind of like a template that I'm going to show you for writing proofs in this section. So let's first talk and walk you through this definition. It says, let f of x be defined for all x is not equal to a over an open interval containing a, and let L be a real number. Then we have the limit as x approaches a of f of x is equal to L. So up to this point right here, all the definition is doing is introducing to you what the letter a represents, f of x, and L is. Okay, so f of x is the function, a is the x value we're approaching, and L is the limit. And this is pretty easy so far. We've seen this already. So they're just making sure that you understand what these letters mean. Now we're going to go down into the harder part down here. It says, for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and a is less than delta but greater than 0, then the distance between the value of the function and the limit is going to be less than epsilon. So that is a big mouthful, and that's usually where students say, what? So we're going to walk you through step by step. Okay, so if you've never seen this symbol before, this symbol here that looks like a backwards 3 is a Greek symbol and is called epsilon. And this represents just a small quantity. It's going to represent a small distance on the y-axis. And that's why we're stating that it has to be positive, because we're talking about a distance. And we don't want to talk about negative distances because that doesn't make sense. Whenever we talk about distances, it should be positive. This symbol right here that looks like an 8 that hasn't been completed, this is called delta. That is also going to represent a small distance, so that also has to be positive. And the delta is going to represent the distance on the x-axis. So let me put in parentheses here that epsilon is going to represent a distance on the y-axis, and delta represents a distance on the x-axis. Okay, so then once we have these small distances set up and they're positive, okay, if we have the distance between, if I pick any value of x And that distance between x and the value of x that we're approaching, that value of a, if that distance is smaller than delta, then the distance between the corresponding y value that we plug in for x is gonna be, and that distance between a corresponding y value and L is gonna be less than epsilon. And that is true if you have this limit. This is the way that we're going to prove that the limit as x approaches a of f of x is equal to L. We use this specific information right here to prove that that limit is true. So let's look at our animation now to get a conceptual understanding of all these letters and symbols. Okay, so one thing I want to point out is that in our book, and when we use the definition of the epsilon delta limit, our book uses a for the value that x is approaching, but this animation here uses x naught. So just keep in mind that this x naught is the same as our a in our definition. It's just the value that x is approaching on the x-axis. So the first thing we're going to do is we're going to create our distance for epsilon. Remember, epsilon is the distance on the y-axis away from your limit. So I'm going to check the box for epsilon. And I'm going to, just for simplicity's sake, keep epsilon at 1. So epsilon is the distance of 1, which means if I have a limit of 2 as x approaches 5, and we can check this. If I put 5 into the square root of x minus 1, that's our function that we're using. I get 5 minus 1 is 4, and the square root of 4 is 2. So that as I approach closer and closer to 5 from either side, I'm going to get closer and closer to our limit, which is 2, which is the value of the function. If I create a distance of epsilon equals 1, that means on my y-axis, I'm going to have an interval that contains my limit that goes out in 1 in either direction. So if my limit's 2, that means I'm going to have a distance of 1 up to 3 and a distance of 1 down to 2. So 2 is going to be in this interval from 1 to 3. Now, I can change this distance by using the slider. So if I want to make it a half, I can make it smaller. And then I only go out to 2.5 and down to 1.5. But for simplicity's sake, I'm just going to keep it at 1. But just know that you can change that distance. If I create my x distance now, I'm going to click on delta. If I have a delta limit of 3, and again, I can change this limit just by sliding the bar. If I have a delta limit of 3, then that means as I get closer and closer to my x value, if I'm in that range of values where I'm 3 on either side of the value of x that I'm approaching for my limit, so the value of x in this case that I'm approaching is 5. If I take away 3 and I add 3 to create my interval, 5 is going to be on the interval from 2 to 8. So if I'm on this interval, I have to be on this interval for this to work, and I get closer and closer to 5 in either direction, I'm going to lie on the yellow interval, so I'm going to be within epsilon of my limit. So, and we can test it. If I check the box here, test. Let's start over here. So if I pick a value within this interval here, within a delta of 3 of my x naught, so I'm in this interval, as I get closer and closer to my value of 5, notice the value of my function, if I come up here, let's say I plug in 3. So I plug in 3, I take the square root of 3 minus 1, I get the square root of 2, and I come over here and that value of the function is within epsilon of my limit. So this epsilon limit definition is all about the distances that we create as we're closing in on our value of x and our value of y to get that limit. As we get closer and closer to our x and our y values, we're creating these intervals so that we can show that we stay within those intervals and we get closer and closer and closer. Okay, so let's walk through our first example. So we want to prove that the limit as x approaches 1 of the function 2x plus 1 is equal to 3. So we're going to use our epsilon delta definition of a limit to prove this. So what we need to prove is that if the distance between x and a is less than delta, then the distance between our function value and the limit is less than epsilon. This is what we need to prove. Okay, so the first thing we need to do is we're going to do some scratch work. We need to figure out what our delta is so that we can formally write the proof. So first we want to do some scratch work to find the delta, and then we formally write the proof. So this is what you need to do for the scratch work to find your delta. You're essentially working backwards to figure out what delta is going to work, so then you can write it up in the correct order in the proof. So we're going to plug in our f of x and our L into this statement here and figure out what, and work backwards to figure out what our delta is. So the main idea, if I plug in my f of x, that's 2x plus 1, and I subtract my limit, which is 3, that needs to be less than epsilon. So now what I need to do is I need to use algebra to find delta by breaking down the statement so that I have it in this form. And then once I see what's over here, I've got my delta. So I need to break down the statement 2x plus 1 minus 3, and I want to break it down to x minus 1 is less than some delta and figure out what that delta is. Okay, so over here, we're going to have 2x plus 1 minus 3 is less than epsilon. Now I want to somehow rearrange this statement so I get something that looks like this. So I'm going to combine and try to simplify this. So I'm going to get 2x plus 1 and subtract 3. That's going to give me a 2x minus 2 when I combine the 1 and the minus 3. I can factor out a 2. And now I get x minus 1 is less than epsilon divided by 2 if I divide both sides by 2. So what I want to do is I want to let delta be epsilon over 2. So we found out what our delta should be in order to make this work. Now we're going to formally write up the proof. So when you write an epsilon delta proof, you want to first start by saying, actually let me label this as proof first. This is our formal proof. We want to first start and say, let epsilon be greater than 0 and delta greater than 0, because we want to make sure that our distances are positive. Then we're going to state what we're choosing for delta. We're going to say choose delta to be equal to epsilon over 2. So whatever epsilon is, we want delta to be half of that. Then the next step, we're going to say assume that the absolute value of x minus 1 is less than delta. Because remember, this epsilon delta proof is basically an if-then statement. we're going to assume the if and show that the then part happens. If this happens, then this happens. So we have to assume the first part happens to show that if the first part happens, the second part happens. So if we look back up here, this is essentially what we're trying to show. This is the main goal. If we have that the distance between the x in our a is less than delta, we want to show that the difference between the function value and the limit is less than epsilon. So we need to assume the if part and show that the then part follows. So that's why we assume that the distance between x and 1 is less than delta. Now we have to show that 2x plus 1 minus 3 is less than epsilon. So we want to show that this is equal to, and this is where the scratch work came in before. We already kind of worked this out. So now we're formally writing it down. This is going to be 2x minus 2, which is equal to 2x minus 1 on the inside of the absolute value. Now, because we know that this here is less than delta, we can then say, well, if I have 2 times the absolute value of x minus 1, and the absolute value of x minus 1 is less than delta, I can make this statement. This is less than 2 times delta. And what did we say delta was? We said delta was epsilon over 2. And if I take 2 times epsilon over 2, I get epsilon. So what we just showed was exactly what we needed to. We showed that this, and if you follow the steps, is less than this. So then we would say, therefore, the limit as x approaches 1 of 2x plus 1 is equal to 3. It works. So the first step is to say that epsilon and delta are greater than 0. The second step is to state what you chose for delta. The third step is to state your assumption. And the fourth step to show that the distance between the value of the function and the limit is less than epsilon. And then the last step is to state, therefore, we have this limit. So we have those 5 steps. Now we can look at this on our graph. So as you can see on our graph, here's our value of a. A is 1. That's what we're getting closer and closer to. And if we draw some dashed lines here, we can see that our limit is 3. Now, whatever we choose for epsilon, if we choose epsilon to be 1, let me change colors here. That means the limit is going to be on the interval from 2 to 3 if we let epsilon be equal to 1. Which means my delta is going to be half of 1, which we said when we figured it out here, our delta is going to be half of 1, half of epsilon, which is going to come out 0.5 in either direction. So if I pick any point as I'm approaching, let me use a different color here now. If I'm approaching this way or this way, any value in this interval will fall in this interval here on the y-axis. And I can keep closing in and making that interval smaller and smaller until it gets so close we can say that the limit is 3. I could choose that epsilon is 0.5, then my delta would be 1/4. So I can keep making those values smaller and smaller and smaller to show that as x gets closer and closer to 1, the value of the function gets closer and closer to 3. Okay, let's look at the second example. We're going to prove that the limit as x approaches -1 of the function 4x plus 1 is equal to -3. So let's do some scratch work to find our delta. So we are going to take our function and our limit and plug it in and then manipulate it so that we can find our delta. So our function is 4x plus 1 and we're subtracting a -3, and this needs to be less than epsilon. So when we simplify this, we're going to get 4x plus 1 and then a plus 3. So we're going to have 4x plus 4 is less than epsilon. I can factor out the 4. And I have x plus 1 is less than epsilon. When I divide both sides by 4, I get that x plus 1 is less than epsilon over 4. And this is what we want to be equal to delta. So we broke it down so that delta is 1/4 of epsilon. So now let's write our formal proof. Okay, so the first step is to state, let epsilon be greater than 0 and delta be greater than 0. Then the next step is to state what we chose for delta. We're going to choose delta to be epsilon over 4. Then the next step is we're going to assume that the absolute value of x plus 1, or the distance between x and -1, is less than delta. We need to show that because the absolute value of x plus 1 is less than delta, we need to show that 4x plus 1 minus 3 inside those absolute values, we need to show that the difference between the value of the function and the limit is less than epsilon. So we have 4x plus 1, and then we have a plus 3 because it's minus a -3. So this actually would turn into a 4. And that's equal to 4 times the absolute value of x plus 1. But because we stated that the absolute value of x plus 1 is less than delta, we can say that this is less than 4 delta. And because delta is epsilon over 4, when I multiply that by 4, I get epsilon. Therefore, the limit as x approaches -1 of 4x plus 1 is equal to -3. We can do a spot check to make sure that what we did makes sense. Let's say I let epsilon be equal to 1, then delta is going to be equal to 1/4. Here's -3, our limit, and we're approaching -1, which is our value of a. If we let epsilon be 1, then we are going to fall between -2 and -4 with our limit, and then our delta is going to be 1/4, so I'm going to come out 1/4 from each direction for the a, which is our -1. And so if I pick some value on that interval between -1.25 and -0.75, then the value of the function at that corresponding value of x should fall on the interval between -2 and -4. So let's just check a value to make sure. Let's say I use -0.9. -0.9 is really close right here. So if I plug that in, we're going to say let x be equal -0.9. If I plug that in to find my value of my function, I'm going to have 4 times -0.9 plus 1, and that's going to give us -2.6. So -2.6 falls right here. So it lies within that interval. And so we can pick a couple other points to make sure. And so any value of x that I pick on this interval here, the corresponding value of y should lie within this interval here. And I can just keep picking those intervals to be smaller and smaller and smaller until it closes in on the limit. Okay, now let's look at our next example. We are going to prove that the limit as x approaches 2 of x squared is equal to 4. What we're trying to show is that if x minus 2 is less than delta, then x squared minus 4 has to be less than epsilon. That's what we're trying to show. If this happens, then this happens. So let's do some scratch work here. Now, when we're trying to find a delta and we're dealing with something other than a linear function, like the previous two examples we did a linear function. Now we're doing a quadratic, we're doing a higher degree, and this is going to happen like if you have a square root or some other function. When you're looking for the delta for some other function other than linear, it takes a little bit more manipulation and you'll have to make more assumptions. So we're going to start with x squared minus 4, an absolute value. We know we want that to be less than epsilon. I'm going to factor this into x minus 2 absolute value times the absolute value of x plus 2. Now we know that this is going to be less than delta times x plus 2 because we're going to assume that this is less than delta. But now the question is, what in the world do I do with this? Because we want our delta in terms of epsilons. So I have to figure out what to do with that absolute value of x plus 2. And this is where we have to make another assumption. We are going to assume that delta is less than or equal to 1. So we can make this assumption because we know these distances are going to get smaller and smaller. So we're going to start off with a delta less than or equal to 1. Now, if we look at our value of a, which in this case is 2, if I know my delta is less than or equal to 1, then I'm going to come out 1 this way and 1 this way. And I know if this is delta and this is delta from here to here, at most, I'm going to get an x value of 3, and the smallest value I would have is 1, because I'm going to fall on this interval. So why is this helpful? By choosing an arbitrarily small delta, it can give us an x value that we can plug in here. So I know that at most, the absolute value of x plus 2 at most is going to be 5, because at most x is going to be 3. And if I plug in 3 for x, I get that at most that absolute value of x plus 2 is going to be 5. So I can say now that this is going to be less than or equal to delta times 5. Since I want the absolute value of x squared minus 4 to be less than epsilon, I have this statement now, and I can say that I found my delta now. Delta is going to be epsilon over 5. We just showed that we can manipulate it so that x squared minus 4 in absolute values is less than epsilon using this information here. Okay, now here's the thing. This is what makes this a little bit tricky. We can't just state that delta for sure is epsilon over 5, because we also made this assumption that delta is less than or equal to 1. So what if epsilon was 6? If we make, and we can do that, if we say that epsilon is 6, if we want our limit to be on an interval that has a distance of 6 on either side, then delta is going to be bigger than 1. And we already made this assumption that delta is less than or equal to 1. So we want to make sure that we pick the smaller of these two, because if we show that it works for the smaller of the two, then we know for sure that it's going to work. So when we write our proof, we actually have to write, because we made that additional assumption, we actually have to say that delta, now let me fix this. Delta has got to be the minimum of 1 in epsilon over 5. Typically, this would be the smaller of the two, epsilon over 5. But there may be an instance where we let epsilon be a lot bigger, and then epsilon over 5 would be bigger than 1. But we don't want that. We want to pick the smaller of the two. So we're going to say that delta is going to be the smaller of these two. So now we officially have our delta, and I'm going to write my proof. Okay, so the first step is to say, let epsilon be greater than 0 and delta be greater than 0. We're going to choose delta to be the minimum of 1 in epsilon over 5. And like I said, I can't stress this enough, typically this will be the smaller of the two unless there's an unusual situation. But we have to add that in to make sure that we're covered, because we did say that delta has to be less than or equal to 1. Now we're going to say assume the absolute value of x minus 2 is less than delta. We want to show that the absolute value of x squared minus 4 is less than epsilon. So I'm going to go through the steps now and break it down. I factored that. Then I said, well, this has got to be less than delta times the absolute value of x plus 2. And since we assume that delta was less than or equal to 1, we know that the absolute value of x plus 2 at most can be 5. And since we know delta is going to be epsilon over 5, or the smaller of the two, that this is going to work, and this is going to be equal to epsilon over 5 times 5, which is equal to epsilon. So we just showed that this is less than this. Therefore, the limit as x goes to 2 of x squared is equal to 4. Now again, you can pick some values and check to make sure that you convinced yourself that it works. So let's say we let epsilon be equal to 1, then delta is going to be 1/5, which is 0.2. So that means we need to pick an x value that is within 0.2 of 2. So if we look here, let me erase this now. Here's our value of a. We want to pick something within 0.2 of 2. So let's choose x to be, say, 2.1. That's within 0.2 of 2. So then if we plug that into x squared, we are going to get 4.2025, and that's definitely within 1 of 4. Our limit is 4, so our interval, if we're at 4 and epsilon is 1, our interval is going to be between 3 and 5. And 4.2025 definitely falls in that window. So this works. So you can do quick spot checks to make sure that what you proved makes sense. Okay, the next example, we have proved that the limit as x approaches -1 of x squared minus 2x plus 3 is equal to 6. So we want to show that if x minus -1 is less than delta, then x squared minus 2x plus 3 minus 6 is less than epsilon. This is what we want to show. So let's do some scratch work. We're going to start with x squared minus 2x plus 3 minus 6. And we want to break it down so that we get x plus 1 an absolute value, because when we simplify this up here, we're going to get x plus 1 in here. That way we can figure out what our delta is going to be. So this gives me x squared minus 2x minus 3, which we can factor as x plus 1 times x minus 3. Now we know that this is less than delta, because that's what we're going to assume. So I can say that this is less than delta times x minus 3. But now we have to figure out what to do with this. And this is where that extra assumption comes in. I'm going to say let delta be less than or equal to 1. And that way when we look at our value of a, which is -1, if I come out 1 in either direction, the largest x value that I get on that interval is going to be 0. So x is going to be less than or equal to 0 or greater than or equal to -2. So since I know x is going to be less than or equal to 0, I can say that this is less than or equal to, and then when I plug in 0, I get the absolute value of -3, which is 3. So I get delta times 3. And I want this to be equal to epsilon. So I'm going to say let delta be equal to the minimum of 1 or epsilon over 3. That way we keep our assumption that delta is less than or equal to 1. But most likely this will be our delta in most cases. Okay, so now that we have our delta figured out, let's write our formal proof. So we're going to start with saying let epsilon be greater than 0 and delta be greater than 0. We're going to choose delta so that it's the minimum of 1 or epsilon over 3. We're going to assume that x plus 1 in absolute values is less than delta. And what we need to do is show that the absolute value of x squared minus 2x plus 3 minus 6 is less than epsilon. That's what we need to show. So we're going to do that by breaking this down. So if I combine like terms here, I have x squared minus 2x minus 3. And I can factor this into x plus 1 times x minus 3 in absolute value. We know that x plus 1 in absolute value is definitely less than delta. And we know at most this is going to be 5. So we can state that the absolute value of x plus 1 times the absolute value of x minus 3 is less than delta times 5, which is equal to epsilon over 5 times 5, which is equal to epsilon. So we just showed that this is less than this. So now we can state, therefore, the limit as x approaches -1 of x squared minus 2x plus 3 is equal to 6. All right, here's our last example. We want to find a delta corresponding to epsilon greater than 0 for a proof that the limit as x goes to 9 of the square root of x is 3. So essentially we're going to write the proof, but specifically the question is asking to find the delta. But we're going to take it one step further and actually write the proof to practice. So we want to show that if the absolute value of x minus 9 is less than delta, then the square root of x minus 3 is less than epsilon. This is what we want to show. So we're going to assume this and show this. Okay, so we're going to start by writing some scratch work. So we're going to start with the square root of x minus 3. Now, this is a little bit different. We have to use some past algebra skills to do some rearranging because I want to rearrange it so that I get an absolute value of x minus 9 somehow so we can figure out what delta is. So what I'm going to do, actually, I'm not going to make that equals. I'm going to make this multiplication. I'm going to multiply the top and the bottom by the conjugate so I can do some rearranging. So I'm going to put that over 1 and I'm going to multiply by the square root of x plus 3 over the square root of x plus 3. So essentially we're really multiplying by 1, but we're doing it in such a way that we can rearrange that square root of x minus 3. So when I multiply this out, I'm going to get on the top x minus 9. And on the bottom, I'm going to get the square root of x plus 3. Now I'm going to carry this down here since I'm running out of room. Somehow, I want to get rid of that square root of x plus 3. I need to figure out a way so that I can write my deltas in terms of epsilon only. So here's what we're going to do. So think back. If I gave you a fraction, say 1 over 3, and I gave you another fraction, 1 over 4. The fraction that has the bigger denominator is actually smaller. Even though the number on the bottom is bigger, we know that makes the whole fraction smaller. So we're going to say that this is less than or equal to the absolute value of x minus 9 over 3. Because no matter what value of x I plug in here, whether I plug in 2 or 3 or 4, if I add it to 3, this denominator is going to be bigger than this denominator, which means this fraction is going to be smaller. So the bigger the denominator, the smaller the fraction. So that means if this is smaller than this, I can write that it's less than. So let me get rid of this clutter now. So basically I can say that that fraction on the right is bigger than the fraction on the left, because no matter what I plug in there, that fraction on the left is going to be smaller because you're going to add something to 3. Now the only value that I could plug in there for x to make it equivalent would be 0. And that's why I also included this equal to here. It could be less than or equal to if I plugged in the point 0 for x. Now I know that this is going to be less than delta over 3 because we said the absolute value of x minus 9 is going to be less than delta. That's how we're making that's the assumption that we're making. And if I want this to be equal to epsilon, then I know that delta is going to be equal to 3 times epsilon. We just chose our delta to be 3 times epsilon. So now we can write out our proof. Officially, we're done with the problem because the problem just asked for us to find the delta. But since we're practicing proof writing, we're going to actually take it one step further and write the proof. So we're going to say, let epsilon be greater than 0 and delta be greater than 0. We're going to choose delta to be equal to 3 epsilon. We're going to assume that the absolute value of x minus 9 is less than delta. And we want to show that the absolute value of the square root of x minus 3 is less than epsilon. So, and we know that when we multiply the square root of x minus 3 in absolute value by the conjugate, we get the absolute value of x minus 9 over the square root of x plus 3. We know because we made the assumption that the absolute value of x minus 9 is less than delta, so we can say that this is less than delta over the square root of x plus 3. We also know that the fraction delta over 3 is going to be greater than or equal to delta over the square root of x plus 3. And if I replace delta with 3 epsilon, I get 3 epsilon over 3, which is epsilon. So we just showed that the absolute value of the square root of x minus 3 is less than epsilon. So then we can write our conclusion and say, therefore, the limit as x approaches 9 of the square root of x is equal to 3. And we are done with that proof. So now that we have a really good solid foundation of limits, when we go into chapter 3 and we start talking about derivatives, you can see how limits are applied in order to derive the concept of a derivative.